Hello and welcome everybody to my screencast today on intersection graphs of rays and grounded segments. I'm Tillman Milzo, or just Till, and I present you joint work with Jean Cardinal, Stefan Felsener, Casey Tompkins and Birgit Vogtenhuber. So this work originated at a wonderful workshop called Order and Geometry in Gotowie, which is somewhere in Poland, and there's a nice palace that you can see here. It was late September, we had a wonderful time, and these are all the participants, and you can see that's me, Birgit, Jean, Stefan and Casey. Okay, so here you can see maybe more clear pictures of all of them. This is Jean from Brussels, and Birgit, she's in Graz in Austria, Stefan, he's in Berlin, and Casey at the Rennie Institute in Budapest, same as me. I'm also in Budapest but not at Rennie. Okay, so let me tell you about the result, and I start with defining what I'm talking about. What are intersection graphs? So given a set of objects, you can define the corresponding intersection graph as follows. If for each object you make a vertex, and if these two objects intersect, you make an edge between them. So here, for instance, this yellow ray intersects this blue ray, so there is an edge between the yellow and the blue corresponding vertex. These are intersection graphs. The intersection graphs we consider today here are the downward rays, grounded segments, grounded one strings, outer segments, and grounded outer one strings. So before I define all of them in detail, they have this common feature that the objects we're considering are kind of attached to something. So here, all these, for grounded segments, all the segments are attached to a line. For outer segments, all the objects are attached to a circle. For rays, this is not so obvious what the ray is attached to, but you can think of those rays as being attached to the circle at infinity, and downward rays to the line at minus infinity. Okay, so this is a common theme, and this is because all these objects have this similarity. The proof will work somehow for all of those. This is a nice thing. So let me now introduce you now the object that we have. The downward rays are rays which go down. Rays are just rays. Grounded segments are segments which are all above some common grounding line. Grounded one strings are a generalization of grounded segments. Here our objects are curves. One endpoint must be at the grounding line, and any two one strings may intersect at most once. That's why one string, and not just string, because any two strings may intersect many times. Outer segments, all segments have one endpoint at the grounding circle, but it is and they must be completely inside the circle. Okay, and they don't have 2 points on the ground circle. Grounding outer one string, similar to the relation between grounded segments and grounded one strings. This is generalization. Here we replace ground segments by one strings, and they again must be grounded. Okay, so these are all the objects we're considering in this talk. So what are the results? So the first result is a complete characterization of the containment relation between these classes of graphs. So we show that grounded segments and downward rays are actually the same thing. We show that downward rays are contained in rays, but strictly contained, so there are some rays which cannot be represented as downward rays. We show also that there's a containment relation between rays and outer segments, but again, this relation is strict, and a containment relation between outer segments and outer one strings. And outer one strings are the same as grounded one strings, and again, this relation is strict. So let me say something to this. So this here, despite the fact that the proof was, I will show you, is very easy, was an open problem by Cabello and Jitsis. I apologize for not being able to pronounce this name properly, but they asked this open problem recently, that these two graph classes are not the same was a conjecture by Cabello. And it was already shown by Cabello and Jitsis, Cabello et al., that those are not the same. So this is not new. One of my co-authors also pointed out that this here is kind of folklore, and we shouldn't claim it as our result. I agree. Okay, I don't know. I haven't seen it before. Maybe been somewhere. Doesn't matter. The important part is now we have the complete characterization. Something has been known before. Something has been conjectured. So it's been asked as an open problem. Okay, so that is result, but that's only the first part of our results. The second part, in order to explain you the second part of our results, I have to explain you this complexity class existential R. As complexity class existential R is anything that reduces a polynomial time to this problem, algorithmic problem, ETR. So what is ETR? ETR is the existential theory of the reals. And what is this? So we have a formula over the reals, which is in Prenix form, and we asked whether there exist real numbers satisfying this quantifier-free formula. And we can use these symbols 0, 1, this variable symbols equal, larger, smaller, equal, plus, multiplication, and, or, not, and so on. So Boolean symbols and arithmetic operations. This is ETR, and anything in existential R is whatever reduces to ETR. So an example, would be this. So does this equation have a solution, and so can I find variables, real numbers, so that this equation has a solution and this equation or this inequality is not true. So here I used symbols which I was not allowed to use, like 12, but 12 is 1 plus 1 plus 1 plus 1 and so on. Same as 5. And y to the 5 is just shorthand notation for y times y times y times y. Yeah, but so this kind of stuff you can express. I don't want to go into all the details, but this is what is ETR. So why is this class important? The importance of existential R. So first note that it's kind of very simple to see that NP is contained in existential R, because it's much more powerful. You have Boolean constraints, but you also have arithmetic constraints. You have variables which can take any value on the reals. In particular, you could restrict them to take only Boolean values, and then this is an easy reduction to such. Much more difficult is the containment of existential R to P-space. And of course, so this is like a major breakthrough, which was because of decades of mathematicians who found better and better algorithms for that. And in both cases, of course, it's not known whether these containment are strict, because if any of them would be strict, we would know that NP is not equals P-space, and that's the major open problem in computer science, so we cannot expect this to know. That we could know this. But I really want to come to the importance of existential R. And here the importance is like a very famous example, which is existential R hard, is segment intersection. So given a graph, we want to know whether we can find a representation of this graph as an intersection graph of segments. So this is what is recognition of segments or segment intersection asking for. And despite the fact that this problem seems very simple, we don't know if it's an NP. So how would you maybe think why this problem could be an NP? Well, you might want just to guess the coordinates of all those segments. And there is a simple argument that you can assume that all these coordinates can be represented by integers, but there's also an example which shows that this precision that you need is 2 to the 2 cn, 2 to the cn bits. This 2 here is too much, but this means that the size of the integer is 2 to the 2 cn, which just means this would be not polynomial size bit length, and this means that it is too large as if you could guess it for some appropriate constancy. And n is the number of vertices of this graph. Okay, so what does it show is, it shows, or actually what happens is segment intersection graph is actually are complete, and meaning that if you would find a better algorithm, if you would show that segment intersection is in NP, then you would show that these two complexity classes are actually equal, and you would show that you can guess, real numbers for arbitrary polynomial equations and inequalities. That would be very strong. So we somehow don't expect, or I don't expect, that segment intersection is in NP. And there are other NP hard existential or complete problems: recognition of unit disks, minimizing the crossing number of a given graph, problems related to linkages. I don't want to explain what are linkages, and there are several questions which might be hard for this complexity class, but one would be rigidity, meaning whether you can move the linkages at all or whether you can draw this at all. Another is pseudo-line searchability, so you have given a set of pseudo-lines and you want to know whether there's an equivalent, where I'm not telling you what means equivalent, set of straight lines. I will come back to that later in more detail. Recognition of visibility graphs. So here, what is a visibility graph? You have tried to represent a graph by points in the plane, and you say any two are neighboring if they can see each other. For instance, this point sees that point. So you put an edge between them, but this point cannot see that point just because there's another point in between. This point is blocking the visibility, so there's no edge between those two. Recognition, if you can find this, again, is existential or complete. And another very famous problem with existential or complete is the Steiners problem for 4 polytopes. So I give you the combinatorial structure of a polytope in R4, and I want to know whether there actually exists such a polytope in R4, realizing this combinatorial structure. This turns out to be, again, existential or complete. So I show you all these problems in order to make you aware of this is not an isolated phenomenon, but several geometric problems are actually not in are likely not to be in NP, and this class existential R seems to capture this hardness very nicely. And all these problems have something in common. They ask for the existence of some geometric objects. Yes. So this is that. Yes. Okay, so what is our result? Well, these 4 classes of graphs, actually these are the same, I told you already, and they're all existential or complete. It's easy that they are in existential R because you can easily encode this using polynomial equations, whether these intersection patterns are realized given a certain graph, but the hardness is much more difficult to show and more surprising. Okay, so now that you know the results and the definitions, for the remainder of the talk, I give you the proof. Okay, let's get started. At first, I'll show you that downward rays and grounded segments constitute the same class of graphs. And the proof is very easy. You need to know projective transformation. If you know projective transformation, it's a piece of cake. If you don't know it, I think it's very difficult. So in the projective, I will not explain you what is projective transformation, but in the projective plane, the mapping xy1 to x minus 1y maps the x-axis, let's assume that this line is the x-axis, to the line of infinity. So the grounded line goes to the line of infinity. And then all of those become downward rays. And it's known that projective transformations are bijective, except some points go to infinity. Okay. This means that, for instance, this intersection will be seen somewhere there as well. Yeah, that's it. Okay, let's go to the next one. Downward rays are a subclass of rays. Well, this is easy by definition because this is graph, like this is in particular a representation by rays. These are special rays, right? So this is easy as well. Rays are subset of outer segment. Let's say I have a ray representation of a graph. Then I can find a really large circle such that all intersections are inside that circle. And then I just cut off the infinite part of those rays and keep those segments, so I have all intersections kept. And I have outer segment representation of the same graph. So that's pretty easy as well. And this also characterizes rays, so there's always a way, if you have a range intersection graph, you can always find such an outer segment drawing such that if you take the line arrangement induced by the segment, then all intersection of the line arrangement is in the circle. Okay, this is the characterization of rays. Then segments are a subset of outer one string. Outer segments are a subset of outer one strings, again by definition, because here any two segments intersect most ones, and this means that any segment is also a one string, and so this is also done by definition. And the last one, outer one strings and grounded one strings. This is very easy. We first do the first containment. So we have here an outer one string representation, and we want to find a grounded one string representation. So we draw a grounded line and we extend all our one strings so that they become one string and they suddenly become grounded to this grounding line. And we can do the same trick reverse. We have this grounded one string representation. We make a new circle around it, and we want everyone to be grounded to that circle, so we just extend everything. Okay, so that's a piece of cake, I'd say. I hope, at least. Yes, so what have we shown? We have shown all those containment relations, except whenever two are unequal, we didn't show it. And there's a reason I showed you all those others before, because they were kind of easy, and those we need more, like, to show that a graph is not representable by something is much harder than to show it is, because you just give this representation. So what we will need in order to show those is a new tool. And I start now to present you this new tool. This is the order forcing lemma. Okay, so we have given a graph, a permutation, and I want to tell you what is a pi-ordered representation of it. So this is my graph, and I have a permutation 1, 2, 3, 4, 5. It's just a simple permutation, and a pi-ordered representation, for instance, by grounded segments, is that all the segments are ordered in that order. So my permutation is 1, 2, 3, 4, 5. So they went along the grounded line. They're in the order 1, 2, 3, 4, 5. And then this is a pi-order representation of this graph. I can have also a pi-ordered representation in case of race. So here the order at the circle at infinity is 1, 2, 3, 4, 5. So yeah, here is maybe already you can notice there's no really, like, where should I start, right? I could rotate it and it would still be, and I could reflect it and it would still be fine. And the same for other segments here. I rotated and reflected it, but still this would be a pi-ordered representation of this graph G. So I hope this gives you enough intuition on what I mean with pi-ordered representation. And now I want to give you a sketch of a proof while, or I first want to say to you the order forcing lemma. So this, now you know what is an ordered representation. So the lemma statement is that if I have a graph G and a permutation pi, then there is a pi-ordered representation of G if and only if this right graph here, which we denote by G pi, is realizable at all. So basically asking whether this graph is realizable at all is equivalent to asking whether this graph has a pi-ordered representation. Yes. So the way that we will use this in the future is we will give a graph and a permutation pi, and we show maybe this graph doesn't have a pi-ordered representation. Well, then this graph G pi obviously doesn't have a representation at all. Yes, this is how we're going to use it. And now I want to show you a sketch of the proof. So the one direction, right? So we have an if and only if. So let's assume that we go the only if direction. So the idea is we extend the representation. So let's say we have this graph, and we have a pi-ordered representation of it at the cycle of segment on the boundary. It's not quite clear how to do this, but you have to be like really close to the boundary that you're not intersecting something else that you don't want. And suddenly you have just graph G pi. Here maybe I haven't put enough segments, but the idea is clear. So this shows if you have a pi-ordered representation of this graph, then you have also a representation of G pi. Okay, so now the other direction. Now I have to show you if I have a representation of G pi, the other graph I have an ordered representation. So, and if you remember, there was this big cycle here in G pi, so we have to talk about cycles. So let's say we have an induced cycle. Then if I have any representation of the cycle, I will notice that there will be a closed Jordan curve here. So I take the first string or segment or array or whatever, and it intersects the second. And now I start from this intersection between, for the second string, I look at the intersection, it has two intersection points, one with the first string and one with the third string, and this will be the first part of my closed Jordan curve. And then for the third string, I look at these two intersection points and I take the part in between, and so on and so forth. And then I have a, this defines my closed curve and an interior of this closed curve and an outside of this closed curve. Okay, how to use this? So that I have this graph G pi, and I assume there's a representation of it, and I know this cycle here induces a Jordan curve. But even more, there are these every now and then, so there will be somehow also curves from here to the grounded circle. Oh yeah, by the way, I show this lemma also only for one case, as the other cases are the same. And what happens is that this defines me regions, because I know this vertex here, it may not intersect any of those. And with those, together with this Jordan curve, I can define regions, and I know that those vertices, they must be in those regions correspondingly. And I know that these regions are ordered along the boundary, and thus also the start point of our red vertices, our relevant vertices, must be ordered the same way. Yeah, and this shows that this, if I now remove all these black vertices from this representation, then I have a pi order representation of this graph. Okay, that's it. So now I use this. Now I use this order forcing lemma. So I want to show you a graph which is a ray graph, but not a downward ray graph. So that's a graph, and this is a permutation. And now I want to show you that this graph is a ray graph first, right? So you can see here I have chosen an outer segment representation, but you can see that I can extend it to ray representation. And I want to show you that this doesn't have a downward ray representation. So it's equivalent to say this doesn't have a grounded segment representation. And in order to do this, I want to use this cyclic symmetry. So you see that basically A and B play the same role as C and D, play the same role as E and F, play the same role as G and H. So this graph is highly symmetric. So when I look at some order on a line, then up to, without lots of generality, up to symmetry, I cut this circle open either here or there. But in both cases, A, B, C, D, E, F gotta be in order on the line. So we draw A, B, C, D, E, F in this order on the line. And now we consider D. So it's not quite clear whether the segment G is on the right or on the left, but it must intersect D, and G is not allowed to intersect one of the red segments. So let's say G is on the right, here denoted by G1. Then in order to intersect D, it needs to intersect this red segment, which is not possible because we see there is no edge between G and any of those red vertices. So we look at the other case that, G is on the other side, then it would needs to intersect B in order to intersect D, and that's impossible as well because G is not allowed to intersect B either. That finishes the argument. So as this doesn't have a grounded segment representation, it also doesn't have a downward ray representation. And we know that these two graph classes are not the same because I just gave you this graph. And note, so if I have this graph and I want to make it and this permutation, so while this graph has 8 vertices, the graph G pi has maybe something like 64 vertices. So our example is very large to show that these two are unequal. It would be interesting to find an example with maybe 10 or 15 vertices, or maybe show that in large class, small examples are these two cases are always the same. Could be. Okay, now I want to show you that rays and outer segments are not the same. And For this, you need to recall this proof that I showed you. So I showed you that rays are not the same as outer segments, are contained in outer segments, because you take a representation and then you just cut off everything. But in particular, this meant that every, so yeah, what does it mean? So if I have a graph G, okay, one step back. So if I have a graph G, then it has, and it's a ray graph, then in particular, obviously it has a ray outer segment representation, but it has an outer segment representation which I can extend again to a ray representation. So let's look at a graph G which is doesn't have a ray representation. This could be, for instance, the case if for any representation I find two segments which are not intersecting, but they form such an angle that if I extend them to rays on in this direction, I will create new intersections. If any representation has this property, that I find two such segments, then this cannot be a ray graph, because I just showed you ray graphs have always one representation where this doesn't happen. Okay, and now here comes the idea. I look at this outer segment graph here, and together with some permutation which forces this order, and then it is clear that the angle alpha and beta, because of those intersections here and those intersections here, both must be smaller or equal to 180 degrees. Because of this, either C and D go together, like it's drawn here, or A and B do. So this means in all representations of this graph here, I have this phenomenon, meaning this is not a ray graph, for any way to realize it. And this means that this graph here is an outer segment graph, but it's not a ray graph. And again, we used this machinery that we could order this. Otherwise, we could draw this segment, for instance, on that side, and suddenly we could flip around this intersection, and these two graphs, and this angle would be larger than 180 degrees. Okay, but we have the order first lemma, so this cannot happen. Okay, and at last, I want to show you that outer segments are not the same as outer one strings. This proof is the one which does not fit on one page. I will need several pages. So let me give you some preparation. So actually I will show something stronger. So I will tell you that it's existential or hard to figure out whether a graph has such a outer segment representation. And I will reduce from stretchability. So I have to show you what means stretchability in more detail than I did before. So in stretchability we have a pseudoline arrangement. So what is a pseudoline arrangement? We have given some x monotone curves. So you see here x monotone curves. Any two are allowed, have to intersect exactly once. You can see this here, any two intersect exactly once, and they must be unbounded. Okay, I didn't draw this here, but you can imagine they go very far up to infinity. And then the question is whether there exists a line arrangement with the same combinatorial structure. And I a little bit dislike the phrasing same combinatorial structure because it's not clear to me what this means. But what is meant is that the phase structure is exactly the same. So you see here, for instance, this gray phase is here adjacent to the green, brown, and dark green phase, and here the same. This gray phase is adjacent to the green, dark green, light green, and brown phase. And this holds for all phases that they have the same incident structure, and this means that these two line arrangements are the same. But there is a different characterization of what means same combinatorial structure. Means the same order of intersection, and we will use this definition. So here, this line, purple line intersects green, brown, red, and here it also intersects green, brown, red. And it's easy to see that these informations, they're the same. So if I know the order that each line, pseudo-line intersects, then I also know the phase structure. And if I know the phase structure, I know in which order each line intersects. So these are the same. But today we will use this, this combinatorial information. Okay, so what will I do? I will, given a pseudo-line arrangement, I will create a graph, GL, and it will hold that GL has a representation if and only if L is stretchable. So I first explain you how to create this graph, GL. So I start with a pseudo-line arrangement, and I cut off, okay, here I already drew it finite, but let's imagine I just cut off. And I assume there are no intersections to the left of it. And then I triple all of those lines in a way that each of those copies behaves as its original member, so no new intersection patterns appear. And then what I will do for each of those triples, let's say here we take the green triple, I will add probes. So I will add probes for each intersection. So the first pair of probes intersect all other pseudo-lines, the second pair of probes only the first two, and the last probe intersects only the first two. So these probes will be useful in order to enforce that I will indeed, that the big green line intersects first the purple, then the brown, and then the red line. And I will do this for all other colors as well. However, I didn't draw it here because then you cannot see anything. I drew it only for the green. Oh yeah, and obviously I don't have just the this. Now this induces me a graph, and it also gives me a permutation because now I can read off here in which order I want to have this. Order I want to have this on this line. I want to have all the segments on this line. Okay. So what I have to show in order to show existential hardness is that L is stretchable if and only if GL is representable as a pi order representation. And I'll show it only for the case that all the objects are grounded to a line. It's a little bit more difficult for everything grounded to a circle, but it's essentially the same. So let's do the only if direction. So assume L is stretchable, then that's the stretching. Again, we can cut off everything to the left. We can treble every line. We can insert those probes. We're done. We found a representation, pi order representation of GL. Again, I haven't added all the probes, but I hope you see the picture. The other direction is a little bit more tricky. So recall that given pseudo-line arrangement, the only information that is important for us is the right order along each line of the other lines. Okay, so assume we have a representation of GL. So we want that first A intersects and then B intersects. So okay, so I've drawn here A. These are the two. This is the actual line that needs to be intersected. We called it here segment. Sorry, called here as. These are the two copies of it, and we know the probes of A. They must be within this gray region here, which is bounded by the two copies of S and B. So now I want that. I mean, there's no problem to add A if I add A here, but let's try to cheat, okay? And let's arrive to a contradiction. We want that A intersects somewhere here. So what's happening is that A needs to enter this gray region to intersect this probe, leave the region, intersect here, enter again this region to intersect the other probe, leave the region again. And obviously this is not possible because here A intersected B 4 times, and yes, this is not possible because two segments can intersect at most once, which is a contradiction. And finish the proof, and this also almost finished my talk. I just want to mention the same holds for circles and rays, and this shows that recognition of any of those graphs is ETR complete. Now this finishes my talk. I thank you for your attention, and these are my co-authors again.